Hi everybody, so we're going to get started into section 10.4 here, areas and lengths in polar coordinates. So we talked about polar coordinates last time in 10.3. I promise this section is not nearly as long as that one was. I know that's a lot of information to take in about a brand new coordinate system, but this one we're just going to look at a couple formulas, do a couple examples, and then that's pretty much going to be it. So let's go ahead and start into this. So we're going to look at a formula for the area of a region whose boundary is given by a polar equation. To do this, we will need to incorporate the formula for the area of a sector of a circle. So this formula here gives us the area of a sector of a circle. So that would be like if I just drew a circle, and here's the center right here, and then I just cut off a piece of it, and I wanted to find the area of this portion right here. So I could find this area using this formula right here. Okay, so we're going to be applying this formula, but not just to a circle, to just any polar curve that we want to. Okay? Alright. So what we have here in our visual, so let me do the picture here first. So let's take a look if I can get this zoomed in here. There we go. Let's take a look at our diagram first so we can really understand what's going on. So here we have our polar axis here. So we have the curve, something like this. This is our curve. R is a function of theta. Okay, because the value of r, the radius from this origin point down here, changes with the function, right? It's not a circle. So if we want to determine the area of this region R in here, then we're going to need to get the area from this theta value, which we're going to call A, to this theta value, which we're going to call B. Okay, so this line here corresponds to theta equals A. This one over here corresponds to theta equals B. Okay, that should be equals, not greater than. Okay. And then our function, the inside, is going to be determined by this r value. So r equals f of theta. And that's going to give us the value of this area. Okay, the area from theta equals A to theta equals B, less than this function. Okay, and the way that we would design this formula, if we were going to actually go through the derivation, is we would do kind of like what we did with the circle. So we would basically just cut this into pieces. We would get an approximation and use that to fill in this chunk of the area, and then we would do that again for the next section, and then the next section, and then the next section, and just keep doing that. If this process looks vaguely familiar, it's because it's how we derived an integral. Right? We derived the formula for integration using rectangular approximations. Right? You approximate the area, and then you take enough approximations, and the area gets closer and closer to the actual area under the curve. But in this case, we're looking at this this polar curve. Okay, so the way that we set up our formula here, the formula for the area of this polar region is going to be the integral from A to B of 1/2 f of theta squared d theta. Okay. This is often, we usually like to use the shorthand because we don't like writing things very much in math. So we go from A to B. This is usually written 1/2 r squared d theta, and this is with the understanding that r is a function of theta. Okay, so these two mean the same thing, just one of them we write r, one of them we write f of theta. Notice this again, the similarity to this formula. Okay, that's kind of where this idea comes from, and you can look, if you want to look in the book, it shows you the full derivation of it, but we're not going to take the time to go through that here. So that's kind of the background here on this formula, but this allows us to now find area of any polar region that we want to. Okay, so let's take a look at an example. So find the area enclosed by one loop of the four-leafed rows, r equals cosine of 2 theta. So for this one, so let me draw the rows. We saw this in the last section. It was one of the diagrams we made. But this one looks kind of like this. That's really bumpy there. Something like that. That's better. Kind of roughly like that. I think I have a better diagram on the previous section if you want to go back and look at it. Or you can just graph that parametric curve. That'll show you exactly what you need. Okay, so we're trying to find the area enclosed by one loop of the four-leafed rows. So we're just looking for one of these here. Okay, so we need to go ahead and section off one of these, and it doesn't really matter which one you pick. Okay, so this is going to be bounded between theta equals negative pi over 4 and theta equals positive pi over 4. Okay, so our formula for the area is going to be integral from negative pi over 4 to pi over 4 of 1/2 times the function squared. So that's going to be cosine squared of 2 theta d theta. Alright, so that's the setup for our integral. Now we can actually use the symmetry of this to help simplify our integral a little bit. So notice it is symmetric about the pole, right, the positive x-axis there. So we can go ahead and just take the integral from 0, so theta equals 0, up to pi over 4, so this portion of it, and then just double that area, and that's going to give us the area of the whole thing. So we take, this is double integral from 0 to pi over 4 of 1/2 cosine squared of 2 theta d theta. Okay. We get the 2 and the 1/2. We can pull the 1/2 out, and it's going to end up canceling with the 2. So this just leaves us with integral 0 to pi over 4 of cosine squared of 2 theta d theta. For this, we need to use the double angle identity. Okay, so 0 to pi over 4. So we have cosine squared of 2 theta. So since 2 theta is the input, we're going to get 1/2 1 plus cosine of 4 theta. So normally if it had just been cosine squared of theta over here, then this would have been 1 plus cosine of 2 theta, right? Because that's the double angle. But because our angle was 2 theta, now our double angle is 4 theta. So that's why we get that one. Okay. And then this is something we can integrate. So we get 1/2 times theta plus 1/4 sine of 4 theta, evaluated from 0 to pi over 4. Evaluate that using fundamental theorem, and this gives you pi over 8. Okay, so we get the area of one of the loops of the four-leaved rows is pi over 8. And that would be the same for all 4 of them, so because it does have that symmetry. Alright, let's look at another one. So find the area of the region that lies inside the circle, r equals 3 sine theta, and outside the cardioid, r equals 1 plus sine theta. Okay, so let me draw this over here so we can get a better visual. Okay. In here. Okay, so the cardioid, see how well I can draw this. Cardioid's going to be something like this. Try this again. Something like that. Okay, so kind of that upside down heart shape. And then this circle is going to be up here, so it's going to actually intersect up here. It's going to come around, hit the origin. I can do that a little bit better. Something like that. Okay, and you can always just go into like Desmos and graph these. I'm just giving you a rough sketch here. But what we're looking for in the question is the area of the region that lies inside the circle and outside the cardioid. So that's going to be this region right here. Okay, so that's inside the circle but outside the cardioid. So in order for us to set up an integral, we need to have bounds. Okay, that's the only way we're going to be able to get this, so I need to figure out where these bounds occur. But don't forget what our variable is here. Our variable is theta, so what we really are trying to find is the angle at which these graphs intersect. Okay, so I'm looking for theta equal to some angle over here, and theta equal to some angle over here, and that's going to give us our boundary. Okay, so to do that, we need to find intersections. So to find intersection points, this is not always easy with trig, especially because you get a lot of possible combinations of points and values, right? Because theta and r, theta can give you a lot of different values that all correspond to the same points. This one's not too bad. We need to set these equations equal to each other, so we get 3 sine of theta equals 1 plus sine of theta. Subtract the sine, we get 2 sine theta equals 1, so we get sine theta equals 1/2. Okay, so there are only 2 theta values in the unit circle that give us sine of theta equals 1/2, and we're both in the right quadrants, so that's a good sign. So these values are pi over 6 and 5 pi over 6. So this value is going to be theta is pi over 6. This one is going to be theta is 5 pi over 6. Okay, and so those are going to be our intersection points. Those are going to end up being our bounds here. Okay, so to set this up, we have a equals the integral from pi over 6 to 5 pi over 6 of 1/2 times f squared. Now, the function, this is one's a little bit different, but it's kind of interesting because when we do integration, so say if I had, right, a function here, a function here, right, well, I guess that one would be f, that one would be g, and if I want to get the area between them, I take the integral of top minus bottom. Right? Hopefully you remember that from very beginning of the course, right? So that was like the first section that we did was area between curves like this. So in this case, we're going to do something similar. So I'm going to take f squared, so the outer curve here, squared minus inner curve squared. And that's going to provide us with that area in between the two. Okay, so that's what we're looking for here. So let's go ahead and set that up. So the outer function is the circle, so that one needs to come first. So that's going to be 3 sine theta squared minus the inner function, which is 1 plus sine theta squared d theta. Okay. So then we can go ahead and just pull that 1/2 out all the way. And then if we do the foiling on this one, okay, so this one gives us 9 sine squared theta. The second one is going to give us 1 plus 2 sine theta plus sine squared theta, and they're all going to become negative. Okay, so let's just combine. We're going to have 9 sine squared minus 1 sine squared, so that's going to be 8 sine squared theta. And again, this is pi over 6 to 5 pi over 6. Okay, and then minus 1 minus 2 sine theta d theta. Okay. So I'm going to do a couple steps here at once, so try to kind of track with me here. This shape, this area also has symmetry to it. So this area from here to here, so this portion is equal to this portion, right? Because they have symmetry about that vertical axis, about the line theta equals pi over 2. Right? That's this one right up here. So this is theta equals pi over 2. So what we can do is just double half of the area. Okay, so I'm just going to take this, I'm going to multiply it by 2, but then that's going to cancel with the 1/2. And this is just going to become pi over 6 to pi over 2. Okay, so again, I'm going only up to pi over 2 now because I'm just taking half of the area and doubling it. And by doubling it, I'm getting rid of the 1/2 because those two cancel. Okay, so hopefully that's making sense. And then in order to integrate this one, we need to use, again, a double angle identity. So the sine squared theta is going to become 1/2 1 minus cosine 2 theta. And then minus 1 minus 2 sine theta d theta. Okay, this is now something that's integrable. Okay, so distribute the 8 to the 1/2, that's 4. Okay, combine any common terms you have. That's going to give you 3 minus 4 cosine 2 theta minus 2 sine theta. So integrate that. You get 3 theta minus 2 sine 2 theta plus 2 cosine theta, evaluated from pi over 6 to pi over 2. And if you run that evaluation, you will find it just gives you pi. Okay, so a lot of work just to get to pi, but just a very interesting result that this area would be exactly pi, right? So just kind of an interesting thing, because pi, of course, is a never-ending decimal, brings up interesting questions about kind of finite area versus infinite area, but those aren't really questions we need to be asking right now. But we got pi. So the area of that shaded region, okay, outside the cardioid but inside the circle, is pi. Okay, so next up, so we're talking about areas. Now we're just going to briefly talk about arc length. So if we want to find the arc length, the length of a curve, with a polar equation instead of a Cartesian equation, then we need to use the formula, the integral from A to B, okay, with theta going from A to B, of the square root of r squared plus dr d theta squared d theta. Okay, so this is our formula for arc length of a polar curve. Okay, so let's go ahead and try an example with this. So find the length of the cardioid. Okay, so the same cardioid we've been working with, let's find its length. So this is going to be L equals integral 0 to 2 pi, and that's again because one rotation around the cardioid goes from 0 to 2 pi. So that's why we set that as our bounds. Square root of r squared, so that's this squared, so that's 1 plus sine theta squared plus the derivative of r squared, so that's just going to be cosine squared. Okay, theta d theta. Okay, if you FOIL this out, it's going to give you 1 plus 2 sine theta. It's going to give you, right, so let me just show that right here. So this is going to be 1 plus 2 sine theta plus sine squared theta. Sine squared plus cosine squared is going to turn into a 1. Okay, so this whole piece turns into 1, so we're left with 2 plus 2 sine theta as our result. Okay, so if you want to pause and mark that down, I'm going to erase it now, just so we can move on to the next step. Okay, so let's do that. So we're going to get 2 plus 2 sine theta by simplifying this algebraically. Alright. Plus cosine squared theta. There we go. Okay, so this gives us integral 0 to 2 pi of the square root of 2 plus 2 sine of theta d theta. Okay. Now, if we want to get any further with this, we're going to have to get a little creative here. So there's a trick that we can do that's going to help us be able to simplify this. And we're actually going to be multiplying this by its conjugate. So this is going to give us integral 0 to 2 pi root 2 plus 2 sine theta times root 2 minus 2 sine theta over itself, because we can't change the identity of the integrand. We have to leave it intact, so we multiply and divide by the same term. Okay, when we do that, so let me show you over here what's going to happen. So the numerator is going to become 4 plus 4 sine theta minus 4 sine theta, right? That's the outer and the inner in the FOIL. And then minus 4 sine squared theta. So this is going to become 4 times 1 minus cosine, or excuse me, 1 minus sine squared theta. Which becomes 2 times the square root of cosine squared theta, which is going to be 2 times the absolute value of cosine theta, like that. Okay, so this is going to be in the numerator, just 2 times the absolute value of cosine theta over the square root of 2 minus 2 sine theta d theta. Okay, and again, I'm going to erase the purple, so you want to write it down, pause it now. Okay. So now at this point, we would need to split this up because the cosine has the absolute value on it, and we can't get rid of that absolute value because we're going over the entire interval from 0 to 2 pi. And there are certain points where cosine is positive and certain points where it's negative. So we would have to split this up over the positive and negative pieces. So if we look right just on the unit circle here, right, here's 0, pi over 2, pi, 3 pi over 2, and then 2 pi, of course, is back at 0 again. Okay. So on this unit circle, if we want to look at where cosine would be positive and where it would be negative, cosine is the x values. So x values are positive all over here and negative over here. So that means if we want to set this up with cosine always being counted positive, right, because that's what the absolute value does, it makes it count positively, we need to split it up into the positives and negatives and make the negatives positive. Okay, so this is going to be integral from 0 to pi over 2. This is a positive piece, okay, of our function. Okay, then cosine is negative from pi over 2 to 3 pi over 2. So I'm going to subtract the negative piece in order to make it positive, right? That's what the absolute value does. So this is going to be pi over 2 up to 3 pi over 2. Okay. Okay. So, and then of the function, so 2 absolute value, or actually, sorry, we don't need the absolute value anymore. Not if we're splitting it up like this. That's the whole point, is to get rid of the absolute value. So 2 cosine theta over root 2 minus 2 sine theta d theta. And then cosine is positive again from 3 pi over 2 to 2 pi. So 2 cosine theta over root 2 minus 2 sine theta. So you can see the integration of this one gets kind of messy. Just bear in mind that the main part that we're focused on, at least for right now, is this, right? Is being able to set it up appropriately. So a lot of this nitty-gritty stuff is just extra practice with methods of integration. And then what you would need to do for all of these is just do a u sub. So you would let u be 2 minus 2 sine theta. Du would be negative 2 cosine theta d theta. And if you do all of that, so make a u sub on all of these, sub back, plug in the corresponding values. I'm just going to tell you what we get. 8. So it turns out it works out to a really nice number. It doesn't seem like that would be the case, but it does. You're welcome to continue doing the integration if you want extra practice with u subs, but that's pretty much, that's going to be what you get.